This is lesson 5.6, entropy. So a spontaneous process is one that just proceeds without any outside interference. For example, if these were two containers full of different gases, clear and yellow, and we open this container, we would know that the yellow gas would slowly diffuse into container A, and that would be spontaneous. You wouldn't have to do anything to get that to happen. However, to go backwards, that would not be a spontaneous process, to go backwards so that all the yellow gas just magically went back into container B. So the reverse of a spontaneous process is a non-spontaneous process. Just because a reaction is spontaneous, however, does not mean that it is fast. It could take days for this reaction to happen, or this process to occur. The entropy is the randomness in a system, and the symbol for entropy is S. So the change in entropy is the S final minus the S initial. The units for entropy are joules per Kelvin mole. So here's an example of entropy. Some of you have bedrooms that look like this. No matter how much you try, the entropy of the universe always seems to take over. Your bedroom always wants to be very random. And the second law of thermodynamics supports your view of your bedroom, because the second law says the entropy of the universe increases in any spontaneous process. So entropy will always increase if the volume increases, if you increase the temperature because the particles are moving faster. If you increase the number of molecules making up the system, the entropy will increase, like if you added a ton more stuff to your room. Entropy will increase when gases form from solids or liquids, because you're going from something ordered to something unordered. If you form a liquid or a solution from a solid, again for the same reasons. If you increase the number of gas molecules during a reaction, the entropy will increase because there's more possible combinations of those molecules. In all of these cases, the randomness of the system will increase. The third law of thermodynamics says that the entropy of a pure substance at absolute zero is zero. Because if you think about this, at absolute zero, nothing is moving. So there's no randomness due to motion. And in a crystalline substance, remember, you have a regular repeating pattern. So everything is completely ordered. So we use calorimetry to find change in enthalpy, but it's much more difficult to find change in entropy. So we use the standard molar entropies, which are similar to the standard enthalpies. They're the molar entropies for substances in their standard states at 1 atmosphere. And this formula should look familiar. The standard enthalpy of formation, the change in entropy is equal to the sum of the moles times the entropy of the products minus the sum of the moles times the entropy of the reactants. So the properties of these standard entropies. Unlike enthalpies, the standard entropy of elements are not zero. The standard entropies of gases will be greater than liquids or solids because they're more random. Standard entropies will increase with increasing molar mass because, again, you get more random. And they increase with the number of atoms in the formula. We can also find the entropy change in the surroundings. Entropy change of the surroundings is equal to the negative enthalpy change of the system divided by the temperature in kelvins. Exothermic reactions are more common than endothermic because negative changes in enthalpy or exothermic reactions lead to an increase in entropy or randomness.